Hello and welcome to yet another video of Cornerstones of Math. In my previous video, which you can check the link in the description, I discussed about so-called intermediate forms in limits. That is, if the limit is given in one of these 7 forms, then two limits that belong to the same form can result in different values. Those 7 intermediate forms are infinity over infinity, infinity minus infinity, 0 over 0, 0 times infinity, 1 to the power of infinity, infinity to the power of 0, and 0 to the power of 0. But when you look at these 7 types, some of you might have the following question. What about 0 to the infinity form? I mean, if the base becomes smaller and smaller, while the exponent becomes larger and larger, then surely the value of limits in this type cannot be determined as a single value, right? Well, contrary to such intuition, the 0 to the infinity type limits are not indeterminate, or should I say, determinate limits. That is, limits of this type all converge to the same value. More specifically, they all converge to 0. This is very interesting property, and I am going to prove this in this video. So we want to prove this statement, and let us express this in a more mathematically rigorous manner. Consider two functions fx and gx having the following properties. As x approaches alpha, the limit of fx is 0, and the limit of gx is infinity. Here, alpha can also be infinities. Then we will consider the limit of fx to the power of gx as x approaches alpha. Here we deal with the case where fx is positive at the vicinity of alpha, because fx is at the base, and when it comes to exponential functions, the base stays positive for most cases. Under this setting, we want to prove that the limit of fx to the power of gx as x approaches alpha is 0. Now this proof requires more advanced or more rigorous way to define a limit. It is known as the Epsilon-Delta definition of the limit, which is as follows. We say that the limit of fx as x approaches alpha converges to the certain value L if, for arbitrary positive number epsilon, there exists a positive real number delta such that for every x whose distance from alpha is greater than 0 and less than delta, the distance between the value of the function fx and number L is less than our arbitrary positive number epsilon. For those of you who haven't learned this college level limit definition yet, this seems all very complicated, but it is actually not that difficult to understand. I'd like to emphasize again that this epsilon, which corresponds to this distance in the figure, is an arbitrary positive number, so we can make this epsilon be whatever small number that we want. The function fx converging to L means that however small this epsilon might be, we can always find this positive number delta so that if the distance between x and alpha becomes less than delta, then the distance between fx and L becomes less than epsilon. Now let's use this epsilon delta definition to the limits given in our problem, the limit of fx being 0 and the limit of gx being infinity. What would be the equivalent epsilon delta statement to these limits? Well, the limit of fx being 0 can be expressed like this. For an arbitrary positive number epsilon, we can always find the positive number delta such that if the distance between x and alpha is greater than 0 and less than delta, then the distance between fx and 0 is less than epsilon. In this problem, we have assumed that fx is positive near alpha because fx will be the base of another exponential function. So if we choose delta so that fx is positive in this interval, then we can say that for every x in this interval, fx is greater than 0 and less than epsilon. Now for gx, the given limit is a diverging limit where the value in this place for 0 is replaced with infinity. how can we express this divergence to the infinity using the similar notation as above? Well, this time, we introduce an arbitrary real number m in the place for epsilon. Then we can say that there exists a positive number delta such that if the distance between x and alpha is greater than 0 and less than delta, then the value of a function gx simply becomes greater than that arbitrary real number m. You can easily understand that this definition makes sense since this real number m is arbitrary, so it can have whatever large value as you want. We will be dealing with fx and gx simultaneously, so we can combine these two statements and simply state like this. For arbitrary positive number epsilon and arbitrary real number m, we can always find the positive real number delta such that if x belongs to this interval, then fx is in between 0 and epsilon and gx is greater than m. So we have this statement, and remember that these epsilon and m are arbitrary numbers, so we can let these be whatever values that we feel convenient. In that sense, I will set the value of epsilon to 1/2 and the value of m to just an arbitrary positive number. Some of you might not get satisfied by setting epsilon to such large value, considering that epsilon can be whatever small value that you want, but in this proof, the main goal is to deal with the limit of fx to the power of gx, and in dealing with this expression, epsilon being 1/2 is small enough and it actually makes the math easier. So in this case, we can say that there exists a positive number delta such that when x is in this interval, fx is greater than 0 and less than 1/2, and gx is greater than m, which is positive. Next, knowing that fx is positive and gx is also positive, we know that fx to the power of gx is greater than 0 and less than 1/2 to the power of gx. And since gx is greater than m, this is less than 1/2 to the power of m. And here comes another important part. This 1/2 to the power of m can get infinitesimally smaller, which has the following interesting implication. Consider an arbitrary positive number epsilon star here in order to distinguish it from previous epsilon. Then we can always find the positive number m so that 1/2 to the power of m becomes smaller than epsilon star, however small this epsilon star may be. Actually, the rigorous proof of this part is also college-level math, but you can still intuitively understand it. Now let me explain the meaning of all this once more. For an arbitrary positive real number epsilon star, which can be whatever small number that you want, we can always find positive number m satisfying this relation, and as for that positive real number m, we can always find positive number delta satisfying these relations in this interval. That is, fx to the power of gx is sandwiched between 0 and an arbitrary positive number epsilon star. And according to Epsilon-Delta definition, this means that the limit of fx to the power of gx as x approaches alpha is 0, concluding our proof. Now, if you're still not comfortable with Epsilon-Delta definition of the limit, you can just think of this result as a result of applying the famous squeeze theorem on this part, using the fact that gx goes to infinity. So there we have it. We have proved that 0 to the infinity type limits always converge to 0, hence it is determinate form, which is an interesting contrast compared to 1 to the power of infinity type, which is an indeterminate form, hence it is not fixed to a single value. Finally, I have said in the earlier part that the conclusion of this video is true when this alpha is either infinity or negative infinity. In these cases, all you have to do is to replace certain expressions of the proof with other expressions, while the logical flow of the proof remains unchanged. And that's all for today's video. Thank you for watching. Please like this video and go check some other videos in my channel, and I will see you in another video.